For years, the semiconductor conversation has sounded almost boringly predictable. America restricts exports. The Netherlands tightens controls. ASML protects its crown jewels. China struggles to gain access. Repeat. That has been the script. And then something happened that didn't fit the script at all. While headlines were focused on advanced AI chips, sanctions, and foundries, Chinese researchers and companies quietly filed nearly 200 patents connected to one of the most difficult areas of semiconductor manufacturing: advanced optical lens systems. Not chips, not processors, not software. Lenses. Which sounds about as exciting as discussing the glass in a camera. Until you realize that modern semiconductor manufacturing is essentially a battle of light. The world's most advanced chips are built using machines that manipulate light with absurd precision. We are talking about systems so accurate that tiny distortions invisible to the human eye can ruin billions of dollars worth of production. And that is exactly where ASML built its dominance. Most people understand that ASML is important because it makes lithography machines. That's true. But it is also incomplete. The machine itself is only part of the story. The real magic sits inside the optical architecture. For decades, ASML and its partner Zeiss refined lens systems capable of directing extreme ultraviolet light with levels of precision that sound almost fictional. Entire engineering careers disappeared into solving microscopic optical problems that most people will never hear about. A scratch smaller than a grain of dust matters. A thermal fluctuation matters. A vibration matters. Every component exists inside a chain where perfection is not a luxury, but a requirement. That is why one number keeps appearing whenever experts discuss EUV lithography. Over 100,000 individual parts, one machine. And buried inside that enormous machine are optical systems that many analysts consider among the hardest technologies on Earth to replicate. Which raises an obvious question. Why would China suddenly file around 200 patents connected to this area? Because patents are expensive. Research programs are expensive. Highly specialized optical engineering teams are even more expensive. Nobody commits resources at that scale without a destination in mind. The easy interpretation is that China simply wants alternatives. Maybe. But I think something more interesting is happening. The assumption in much of the Western discussion has been that semiconductor power comes primarily from controlling chip fabrication nodes. Control the fabs, control the future. There is logic to that argument. Yet if you look closely at the supply chain, another reality appears. Every advanced semiconductor breakthrough eventually runs into a manufacturing bottleneck, and manufacturing eventually runs into optics. The deeper you travel into modern chipmaking, the less this becomes a story about silicon, and the more it becomes a story about controlling light itself. That shift changes how we should view China's patent activity. Because patents are often treated as evidence of invention. Sometimes they are. Other times they are evidence of intent. Think about it this way. If someone starts buying land around a future airport before construction begins, they're not reacting to today's reality. They're positioning for tomorrow's. Those 200 patents may represent something similar. Not proof that China has solved ASML's hardest problems, not proof that EUV dominance is about to collapse, but evidence that Beijing understands exactly where the bottleneck sits. And if that's true, then the conversation moves far beyond sanctions. A lot of people assume China's challenge is catching up in chips. I'm increasingly convinced the more important question is whether China is trying to redesign the ecosystem around those chips altogether. There's a difference. A very big difference. Because once a nation starts targeting the bottlenecks beneath the bottlenecks, the timeline changes. And the story becomes much harder to predict. The interesting part is that this isn't the first time a technological monopoly looked untouchable right before a competitor began attacking its foundations. We'll come back to that. The easiest mistake to make here is assuming that all patents are equal. They're not. A patent can represent a breakthrough. It can also represent a defensive position, a research direction, or an attempt to secure options for the future. That means the headline number, 200 patents, isn't the important part. The important part is where those patents are concentrated. When researchers started examining China's optical research ecosystem over the last several years, a pattern began to emerge. Universities, state-backed laboratories, and private firms weren't all chasing the exact same target. Instead, they were attacking dozens of smaller problems that collectively sit inside advanced lithography systems. Optical coatings, mirror stability, aberration correction, alignment systems, precision metrology, thermal compensation. None of these sound dramatic on their own, yet neither does a turbine blade when you're discussing jet engines. The value comes from the system. One component alone rarely changes history. A collection of improvements often does. This is where many discussions about semiconductor sanctions become strangely simplified. People tend to imagine technology as a single wall. Either you can climb it or you can't. Reality looks more like a maze. Block one path and engineers start searching for another. That's exactly what happened in several industries throughout modern history. Japan's automotive industry faced skepticism in the 1950s. South Korea's memory manufacturers faced skepticism in the 1980s. China's solar industry faced skepticism in the early 2000s. None of these sectors followed a straight line. They improved through thousands of small gains that eventually became impossible to ignore. The reason I bring this up is because ASML's strength wasn't built overnight either. Many people see today's company and imagine an uninterrupted march toward dominance. The actual story is messier. ASML spent decades solving problems that often appeared insignificant at the time. Engineers would spend years reducing tiny errors that measured fractions of a micron. Outside observers barely noticed. Then suddenly those accumulated improvements became a moat nobody else could cross. That's how technological leadership usually works. The public sees the castle. The engineer spent 30 years digging the moat, which leads to an uncomfortable possibility for anyone assuming export controls alone can freeze technological development indefinitely. What if China's objective isn't copying ASML's moat? What if it's building a different route around it? That's a harder question, because even critics of China's semiconductor ambitions acknowledge something important. Beijing has demonstrated extraordinary patience in strategic industries. The National Integrated Circuit Industry Investment Fund, often called the Big Fund, has directed tens of billions of dollars into semiconductor development over multiple funding phases. Provincial governments added more capital. State laboratories expanded. Universities increased specialized training programs. The results have been uneven. Some projects failed. Some became corruption scandals. Some burned through money with very little to show for it. That part is real and shouldn't be ignored. But failure inside a massive technology program does not automatically mean the overall effort is failing. Sometimes it means thousands of experiments are occurring simultaneously. Most will go nowhere. A few matter. Remember the optical bottleneck from earlier? There's a reason I keep returning to it. Even if China cannot immediately replicate the most advanced EUV systems, improvements in supporting optical technologies can still produce meaningful gains across older lithography platforms. And that's where the conversation becomes more practical. A country doesn't necessarily need to reach the absolute frontier tomorrow. It only needs to move the frontier closer. 5 years ago, many analysts argued China would remain heavily dependent on foreign semiconductor technology for the foreseeable future. Then Huawei released advanced processors that weren't supposed to arrive when they did. The reaction was fascinating. Some observers treated it as proof that sanctions had failed. Others argued it was merely a temporary achievement. I think both interpretations miss something. The processor itself was important. The engineering ecosystem behind it was more important. Because ecosystems learn. Factories learn. Researchers learn. Supply chains learn. And once learning compounds, predictions become dangerous. We'll need that idea for what comes next. because the biggest misconception surrounding ASML's optical advantage isn't that it's impossible to challenge. It's that the challenge must look exactly the way people expect. For a long time, the semiconductor discussion has been framed almost like a race. Who is ahead? Who is behind? Who caught up? Who fell back? The problem is that technology rarely behaves like a race. It's closer to an ecosystem. And ecosystems can change direction in ways that aren't obvious until years later. This is where I think the conversation around ASML, China, and those optical patents becomes genuinely interesting. Because the real question may not be whether China can build an exact copy of ASML's machines. The real question is whether future semiconductor manufacturing will require the exact same architecture that ASML dominates today. Those are very different questions. Consider what happened in computing. IBM once controlled enormous portions of the computer industry. Then the industry shifted. Microsoft became dominant. Then mobile computing emerged. Apple and Android reshaped the landscape. The winners of one era did not automatically become the winners of the next. Technological leadership is powerful. It is not permanent. That doesn't mean ASML is in danger today. Far from it. The company remains years ahead in several critical domains, particularly in high-end optics, precision engineering, and system integration. Many semiconductor experts believe reproducing ASML's most advanced EUV capabilities could take competitors a decade or more. Some argue even longer. And honestly, I understand that argument. When you look at the complexity involved, it sounds reasonable. Remember that number from the opening. More than 100,000 components inside a single advanced lithography system. Thousands of suppliers. Decades of accumulated expertise. An entire industrial ecosystem built around microscopic precision. You don't recreate that overnight. You don't recreate it with money alone. You don't recreate it simply because a government decides it wants to. But here's the reversal. History suggests that dominant technologies are rarely defeated by direct imitation. They're often challenged by alternative approaches. Railroads didn't disappear because someone built better railroads. Air travel changed the equation. Mainframe computers weren't defeated by larger mainframes. Personal computers created a new path. Film photography didn't lose because someone made better film. Digital imaging changed the rules entirely. That's the possibility sitting quietly underneath this patent story. Not certainty. Possibility. And it forces us to think differently. What if China's researchers are not simply trying to duplicate existing optical systems? What if some of those patents represent attempts to solve manufacturing problems through different engineering pathways? I want to be careful here. There is no evidence that China has suddenly discovered a magic shortcut. Anyone making that claim is getting ahead of the facts. Yet there is also very little evidence supporting the assumption that today's semiconductor production methods will remain frozen forever. Technology evolves. Constraints evolve. Manufacturing evolves. And sometimes, bottlenecks that appear permanent turn out to be temporary. One underappreciated example comes from advanced materials. Over the last decade, Chinese research institutions dramatically increased their output in optics, photonics, precision materials, and semiconductor-related engineering disciplines. Not every paper matters. Most never will. But volume creates probability. The more shots on goal you take, the greater the chance that one of them changes the game. This is why I find the patent story more significant than many headlines suggest. Not because patents equal success, they don't, but because patents reveal where attention is being directed. And attention is one of the earliest indicators of strategic intent. Governments can hide projects. Companies can hide prototypes. Engineers can work in secrecy. But large-scale research priorities eventually leave fingerprints. The patent trail is one of those fingerprints. A surprisingly visible one. There's another layer that often gets overlooked. The sanctions themselves may have accelerated some of this activity. That's not an argument against sanctions. It's simply an observation. Pressure changes incentives. When access becomes uncertain, self-reliance becomes more attractive. When critical technologies can disappear through export controls, governments start asking uncomfortable questions about dependency. China is not the first country to react that way. It won't be the last. In fact, one of the more ironic aspects of this story is that both sides may believe they're acting defensively. Washington sees export restrictions as protecting technological leadership. Beijing sees domestic development as protecting technological security. Each side views its actions as rational, which means neither side is likely to stop. And that's why this story extends far beyond optics. The patents matter. The lenses matter. The lithography machines matter. But beneath all of them sits a much larger contest over who controls the foundations of future technology. The answer isn't clear yet. What is becoming clear is that both sides have already decided the struggle is worth decades of effort. And once nations begin thinking in decades instead of quarters, the outcome becomes far harder to predict than most headlines suggest. Let's go back to the question we opened with. Why would China spend years building patent portfolios around optical technologies that many people outside the semiconductor industry have never even heard of? I don't think it's because Beijing believes it has already solved ASML's advantage. If that were true, we'd see evidence elsewhere. We don't. ASML remains the dominant force in advanced lithography. Its partnership with Zeiss remains one of the most sophisticated engineering relationships in modern industry. The barriers protecting that position are real, and they're enormous. But dominance and permanence are not the same thing. That's the distinction that matters. When analysts focus only on today's technology gap, they often miss the more important question. What will the gap look like 10 years from now? Because 10 years is an eternity in engineering. The engineers entering Chinese optics programs today may become the lead researchers of the 2030s. The laboratories being funded today may produce breakthroughs nobody can predict. Most won't. A few might. And that's usually enough. One thing I've learned from watching technology industries is that the future rarely arrives through a single dramatic breakthrough. It usually arrives through thousands of small improvements that suddenly become visible all at once. From the outside, it looks sudden. Inside the industry, it never was. The semiconductor world has seen this before. Taiwan wasn't always viewed as indispensable. South Korea wasn't always viewed as a memory powerhouse. ASML itself wasn't always viewed as an untouchable giant. Those positions were built gradually. Then one day, they appeared obvious. I suspect something similar is happening with China's optical research effort. Not necessarily a coming victory, not necessarily a coming failure. Something more important than either of those. A long-term capability build. And capability is harder to measure than products. Products can be counted. Capabilities reveal themselves years later. That's why I think many discussions about sanctions miss the deeper story. The debate often becomes emotional. One side argues the restrictions are working. The other argues they are failing. Reality is probably more complicated. The restrictions have unquestionably created obstacles. They've slowed access to critical technologies. They've increased costs. They've delayed progress in several areas. At the same time, they've also created powerful incentives for domestic alternatives. Both things can be true simultaneously. History is full of examples where technological pressure slowed a competitor in the short term, while motivating adaptation in the long term. The outcome usually depends on whether that adaptation succeeds, and that's the question hanging over this entire story. Not whether China has matched ASML today. It hasn't. Not whether 200 patents automatically change the industry. They don't. The real question is whether those patents represent the early stages of an engineering ecosystem that eventually becomes self-sustaining. I'm not completely certain. Anyone claiming certainty here is pretending to know the future. What I can say is that the pattern deserves attention, because technological competition is rarely won by chasing the visible prize. It's often won by identifying the bottleneck everyone else takes for granted. That's why I keep coming back to the optics. Not the chips, not the processors, not even the lithography machines themselves. The optics. The hidden layer underneath the hidden layer. The place where a tiny distortion can determine whether a trillion-dollar industry advances or stalls. And if China's researchers truly believe that's where the bottleneck sits, then those 200 patents may tell us less about where China is today and more about where it intends to be a decade from now. My prediction? ASML will remain the global leader throughout the remainder of this decade. I don't see evidence suggesting otherwise. But I also think the next chapter of the semiconductor race will look very different from the last one. The battle won't simply be about manufacturing chips. It will be about controlling the technologies that make manufacturing possible in the first place. That's a much bigger contest, and a much longer one. If you're watching this industry closely, don't just follow the latest processor launch or the latest sanction announcement. Keep an eye on the bottlenecks. They're usually where the future shows up first. And sometimes the most important story in technology isn't the machine everyone can see. It's the lens hidden inside it. If you enjoyed this deep dive, stick around for the next one. There are a few more quiet shifts happening in the semiconductor world that deserve far more attention than they're getting. And somewhere in a laboratory, an engineer is probably filing another patent while the rest of us are still arguing about the last one.